Okay, thank you for the introduction. So I'll be talking about machine learning with Apache Spark. I come from SV Group, company in Zagreb. We're about 40 people working with big data. We have Spark projects and so on. I'm organizing Apache Spark Zagreb meetups in Zagreb, monthly meetups. I'm trying to do it monthly. And on this lecture, I'll be giving 3 free ebooks from my book, Spark in Action. That's at the end of the lecture. Also, many publications, the publisher gave the special discount code for all of their books. These are just some of the data science books from Manning. You can get a 39% discount for all of the books if you'd like. So agenda for today is the what is Spark and how does Spark work, a general introduction to Spark for those of you who haven't been to my last lecture. Then I'm going to talk generally about machine learning. I think most of you are already familiar about machine learning, but nevertheless. And then I'm going to talk about, obviously, using machine learning in Apache Spark. And I'm going to say a few words and slides about other machine learning frameworks that are sort of compatible with Spark and be used with Spark. So please indulge me first, if you could raise your hand if you've never used Spark before. All right, thank you. If you've played around with it on your laptop, thanks. And you're planning or using it in production, thank you. Several hands, okay. Thanks. So what is Apache Spark? It's a distributed, general purpose, large scale data processing engine. So it's a distributed, which means obviously it runs on many machines in a cluster, and the computations on Apache Spark are parallelized. It's general purpose, which means that it can be used across different industries, such as astrophysics, from astrophysics to banking and telecommunications and other industries. It's a large scale. When we say big data, we think of Facebook, Twitter, and LinkedIn, and so on. But obviously, there are some other, usages for some other environments where you have really huge amounts of data, which doesn't have to be those huge companies. As several people said, I think Bojan last night said that you don't really need to have a distributed framework. Sometimes it's a relational database is just enough. If your data fits inside one machine, then you could probably make a set of clever Linux scripts or use a relational database or a C# Java program to process your data much quickly, not too much quickly, but quickly than using a distributed framework, because having a distributed computation necessarily involves a certain overhead of orchestrating the workload inside the cluster. And it's a data processing engine, which means it's about processing data, and it's not for storage. You don't store data inside Spark. You don't visualize data using Spark. You use other third-party tools to do that. It's for processing data and most likely for batch processing, or you can do it with real-time data, but it's not for OLTP, for example, for online transactional processing, where you need to update little bits of pieces of data all the time. Why would you use Spark? So Spark is fast, which it's been its main selling point since its inception, like 3 years ago, because it overperforms MapReduce. It can be 100 times faster than MapReduce because it caches data in memory, works mostly in memory, and especially for iterative tasks such as machine learning, where you use the same data over and over again in iterations. That way, Spark can reuse the data from memory directly. It doesn't have to read it from the external storage every time. So it broke the world sorting record for sorting 100 terabytes of data in 20 minutes on 200 machines, whereas Hadoop it took several hours with 2,000 machines. It has a simple and concise API, so it's functional programming with Scala, Python, which is a good fit for those kind of tasks you do with big data when you process big data and group data and transform data. For example, MapReduce program for word count, it took 3 classes, whereas in Spark you need just a couple of lines to do it. It's really expressive way of doing things. It's a unifying platform, which means that it contains API for batch processing, real-time processing, and machine learning, graph algorithms, and SQL querying data, and you can execute standard NC SQL commands and query data inside Spark. So in the same environment you have all of those different functionalities, which means you can, if you invest in putting Spark in your organization, your people have already knowledge, and they can work in the same environment for many different types of tasks. And finally, Spark has gone mainstream. It's part of all major Hadoop distributions today. All big companies are using Spark for various reasons. For example, IBM, half a year or a year ago, decided to commit 3,000 developers to Spark. They opened up a Spark Technology Center in San Francisco, and they have been integrating Spark inside their products and so on. So it's really, the community is huge, and the speed at which it's developing and improving is mind-boggling, really. I had to update the book several times just to keep it updated. That's why it was supposed to come out last month. So this is the basic architecture of Spark. Your mental image of what we're talking about. You got some client JVM, which runs a driver process. Driver process is the main entity that takes care of asking the cluster manager to bring up a set of Spark executors, and it communicates with them, distributing workloads to be done on the data. The cluster manager can be a Spark standalone cluster. This is just a logical image. This doesn't show the physical machine. This can be just one machine, cluster on your laptop, or it can be a distributed 5 machines or whatever. So these executors are just also JVM processes, Java processes. They have their own Java heap and a set of task slots which can be used, which are just Java threads for using tasks in parallel. So these white ones are vacant, and the blue ones are tasks executing. The Spark components are, these are parts of Spark API. The Spark core, which works with RDDs, which are distributed collections. Then there's Spark SQL, which uses data frames, and data frames are used for working with structured data. Data frames have defined a set of columns on the data with types of columns, whether they're nullable or not, which is a kind of schema, similar to relational database. You can register data frames and query them with SQL and simple standard SQL. Then there's Spark Streaming for working with real-time data, which is in Spark 2.0 you work with, there's a structured streaming that came out, which is, it also uses data frames, and you program it exactly the same as you would on a batch program using data frames, but then you add one line and it auto incrementalizes the computation, so it works in real time. There's also GraphX for working with data organized in graphs, and there's machine learning libraries MLlib and ML. So, machine learning with Spark. First of all, what is machine learning? I guess you know, but I like this definition. It's a scientific discipline which explores the construction and study of algorithms that can learn from and make predictions on data. Those two gentlemen came up with this definition in '98. And machine learning relies on methods from the fields of statistics, probability theory, information theory, and computer science, obviously, to discover and use the knowledge inherent in the data. So it's different than the traditional programming methods of when you make a program to do exactly one thing, display something to the user, react to user input or something. In the case of algorithms in machine learning, the behavior changes based on the knowledge in the data itself. So the basic classification of machine learning algorithms is to supervised and unsupervised learning algorithms. So this is the famous iris flower data set, which tries to classify iris flowers based on the length and width of the sepal, those little green things on the flowers below the lattices. So the length and width of the flowers are measured, and then you can see that some of the iris flower types have different combinations of those two input features. On the left-hand side, those input examples are categorized in advance. So you know in advance to which category each example belongs, which flower it is. On the right-hand side is the unlabeled examples. So the algorithm needs to find out not just, it needs to find out also the groups, what number and what types of groups there are in the data. It doesn't know in advance. So that's unsupervised. For example, that's, for example, customer segmentation. You want to know what kinds of customers you have. You don't really know how in advance how they are, what differentiates one group of customers from the other. So you apply an unsupervised learning algorithm to also find out what distinguishes one group of customers from the other. The other classification of machine learning algorithms is to regression and classification. It depends on the type of the target variable. So the variable you are trying to predict. And on the left-hand side, you see this is an example of linear regression because the line is linear. There's only one input feature or dimension on the x-axis, and the target variable is on the y-axis. You want to find the most probable value given the x value, most probable value of y given this set of input examples. So probably linear regression is not a very good fit here. Some kind of curve would fit this data maybe better. So, so this is a regression problem because the target variable is continuous. It's a continuous number. And classification, that's the iris data set because there are two features here, and the target variable is the category itself. So there are only the target value is distinct. It can take just a limited number of values. And the machine learning is not just about employing machine learning models and algorithms. It's also about collecting different types of data, parsing documents and binary data, audio, video, and so on. Then you need to clean up the data, prepare it for visualization and analysis. And for example, you would need to decide, sometimes there are missing values in your data. People didn't fill in a form year of birth, for example, or something. So you have to decide what to do with those examples. Do you discard them? Do you replace those missing values with some average values, or do you build a machine learning model to see what value would fit there, and so on? Then you probably need to scale the data because many machine learning algorithms need to work with data that's in similar ranges, so that one feature doesn't affect the algorithm too much. And probably you will need to have the data, all the features have the same mean. And what else? You would need to replace the string values with some kind of numeric values, because algorithms don't work well with strings. You need some kind of numeric value for the algorithm to work with. And when you have your data cleaned and prepared, you would do some kind of exploratory analysis to see what do you have in your data, some summary statistics, maximum, minimum value, average, some histograms, and are some dimensions correlated or not, and so on. Then you would use some kind of visualization to have a feeling of the data, what to do with it, and how to get some value from the data. You would pick the training algorithm, machine learning algorithm, train the model, and then evaluate its performance to see does it work well, does it predict the target value well or not. And if it's not good, you would go back and maybe add some new dimensions, get more data, or pick a different algorithm or something else. Or you would put your model in production and get some value from your model. And the point is that Spark is such a general framework that you can use it for most of these tasks, except for visualization maybe. It's integrated in R, so you can use it for R ggplot library for visualizations and so on. There are two main sections of the Spark API. There's MLlib and ML. MLlib is the original Spark library, and ML is the new one. Since Spark 2.0, that's the default main machine learning library. I'll say a few words about each of them. MLlib is RDD based, so RDDs, those of you who haven't been on the previous lecture, RDDs are resilient distributed data sets, which are distributed collections. They are lazy. There are transformations. You can make new RDDs from existing ones, map, reduce, group by key, and so on. But those are for unstructured, mostly for unstructured data. Spark MLlib has distributed matrices and vectors, implementations, and as I said, 100 times can be faster than MapReduce if the data is cached. It has most of the most popular algorithms, implementations, so most popular machine learning algorithms inside the library for feature transformation, summary statistics, PCA, linear and logistic regression, support vector machines, naive Bayes, random forests, gradient boosted trees, and k-means clustering, and others, TF, IDF for document discovering topics, and so on. This is several examples of code excerpts from for using MLlib API. Those are, by the way, from my book. If you'd like, you can play around. I have the data sets and the complete code at the GitHub site. I'll show you the link afterwards. So you need to, most of the machine learning algorithms in MLlib work with RDDs containing labeled point elements. So labeled points have, the first element here is the label itself, and the features, input features, are contained inside vectors. So this is there are dense and sparse vectors. So never mind those. So you first have to have an RDD of labeled points, and then you can use, for example, splitting the data is very simple. You normally need a training data and testing or validation data, and sometimes a ratio of 80% to 20% is used. So it's very simple to split the data randomly to training and validation sets. You can use, some people use 70, 30% or... So this is a scalar. when you need to scale the data, you construct a standard scalar object, and you tell it, do you want to scale the ranges of the data, and whether you want to move the means of the data so that all the features and dimensions have the same mean of about 0. So in this case, it's both true, and you have to fit the model based on the training data set so that it finds the maximums, minimums, and what to do with all the features. And then you get the model, and then you map all the data using this model, scalar model, to transform the features to the new ones. So it's then scaled. You do it for the training data and validation data, and then if you put it in production, your model, you need to scale your real life data before using the model, which was trained on scale data, right? Then this is an example of linear regression with a stochastic gradient descent, which is not really important now. Most of the algorithms in MLlib API work mostly the same. So you create an instance of the algorithm, put some parameters for the algorithm, for example, maximum number of iterations you want it to run. You have to cache the data before using the algorithm because it's iterative, and then just call run. So some algorithms you call fit method, for some you call run. It's not standardized. And when you have your model, then you would map your validation data to have tuples containing your prediction for the example and the original label. And when you have those together, then you would use some kind of metrics object for evaluating the model. In this case, regression metrics, which would take those predictions and labels and calculate the amount of error. For example, root mean squared error, which is standard way of evaluating regression models. Spark ML, on the other hand, is data frame based, which means that it has some performance improvements, especially since Spark 1.6 and 2.0, because it doesn't use Java heap that much. It allocates memory off heap, and it serializes, doesn't use the default Java serializer, it binary serializes the data, so it can be faster. And that's this Tungsten project, which brought these improvements. And it also uses the catalyst optimizer for optimizing the query plan to how to access the data when you're joining or doing whatever you're doing with the data frame data. Catalyst optimizer is used to optimize the plan, just like in a relational database. So it's faster than MLlib, and Spark ML brought machine learning pipelines, which you can use to chain several models together, and you train them and use them, evaluate them together. Together as a unit. So I'll show you an example. So this pipeline model is just another transformer. So the classes inside Spark ML have been standardized. So these are the main interfaces in Spark ML API. So you have an estimator, which is used for fitting a model. This is your machine learning algorithm. You call fit method on it to produce a transformer, which is a model, which then transforms the data to get your prediction. And then you have a evaluator, which then evaluates the model using the original data set and the transform data set. So also, the list of algorithms is more or less the same as the MLlib. It doesn't include deep learning convolutional networks yet, but I'll show you a couple of frameworks you can use with Spark, which do. So this is an example of using ML API. Similar, you create a instance of, in this case, logistic regression algorithm. There are two ways to set the parameters. You can do it on the object itself or inside the fit method, which has been also standardized. So each parameter has its own unique code. So you can when you're using pipelines, you can give a different set of examples for each run of your algorithm, which is something you do often with machine learning. You want to do how does it do with I don't know, 200 iterations or 500 iterations. You need to rerun the same algorithm with different parameters several times. This is a standardized interface method fit, and then you would call transform on your model, which is a transformer, not the transformer from the movie, but the transformer from the API. And then you would get your predictions, and you would use a binary classification evaluator to get the value for a metric. In this example, this classification metric area under receiver operating curve, which is sort of standard with classification models. This is an example of using the pipeline. In this case, there's a scalar model which takes a column of features and adds a new column with scaled features. This is the, do you want to scale the ranges, or do you want also to scale the mean? And then a different estimator is constructed for logistic regression, and it will use the scaled features as an output from the first one. And you parameterize it with different parameters, and then you construct a pipeline and set both the two stages, and then use this pipeline as an estimator itself. You fit both of these estimators to produce a pipeline model, which contains both of the models together, or both of the transformers in ML terms. And then you use the transformer to transform the validation data. You get your predictions, and then evaluate using the evaluator as before. So the other, I decided not to go into, not to do the demo here, because it's always complicated. But I'm going to show you some other compatible frameworks you can use with Spark, or which are somehow connected with Spark. Mahout is an older framework which used MapReduce, so it was much slower. And they decided like a year ago to move to Spark, to abandon MapReduce and move to Spark. I'm not sure how far they've gone. The last time I checked, I think the project wasn't that busy. So I'm not sure if it's got much future. I don't know. Then there's H2O with sparkling water. I have a chapter in the book about H2O, and I'm going to show you some slides because I like this framework. H2O is not Spark specific. It can run by its own, but you can use sparkling water, which is a addition. Yeah, who comes up with these names? Sparkling water is like a bridge between Spark and H2O. You can use it to run an H2O cluster inside the Spark cluster. Then you would use Spark for data preparation, cleanup, and so on, and transfer this data to H2O, and probably use, I don't know, deep learning algorithm on H2O, or they got now in the latest version, they got convolutional networks also. So it's nice. Then there's SparkNet. You can use Caffe framework with Spark. Caffe also has, it's for mostly for image data processing, convolutional networks, and it can use GUI graphical processors for doing it. And there's DL4J, which is very present on internet, deep learning for J. But honestly, I don't think it's My opinion and feeling is that only few people are maintaining this project, and the API is kind of confusing, and I don't recommend it. If you need deep learning, it's better to use H2O, I think. Then there's XGBoost for J. XGBoost is extreme gradient boosting, and they say that more than 60% of Kaggle computations is won by this with this algorithm. So might be interesting. Spark has gradient boosted trees, but not XGBoost. So maybe you'd like to check it out. So this is a couple of screenshots from H2O. When you bring up your cluster, H2O cluster inside Spark with sparkling water, you get the Flow UI, which is a nice tool to visually do building. You can build your models and train them and use them from just by clicking. All the things you can do through the Flow UI, you can do the equivalents with sparkling water API in Scala or Python R. So you can import files, you can get frames, they call data frames, they call them frames, sets of data. You can see what jobs are running, you can get predictions, build models, and so on. This is an example of, it shows you, there's just one instruction to get frame summary for housing, for example, and you get summary statistics for all the columns, minimum, maximum, mean, and so on. You get automatically, it displays histograms of the columns. You can split frames very easily. You can build a model. In this case, it's a deep learning model. You just say what's the training frame, what's the validation frame, what's the target. It's not shown here, but what's the target column? Here it is, response column. And it automatically detects if it's a regression or classification. So it, I'll show you an example. It shows the job as running when you're building the model. And those are the metrics of evaluation metrics of the model. And it was automatically discovered if it's regression or classification. So this is an example of showing the deviance, validation deviance and training deviance. This is ROC curve shown automatically also. And that's about it, yeah, about H2O. So if you want to know more, you can find the code and example data sets on the GitHub repository. And if you buy the book by any chance, those are chapters 7, 8, and 14. Yes, we are hiring SV Group from Zagreb. If anybody wants to relocate to Zagreb or is from Zagreb, please come and work on Spark and Big Data. To repeat the discount code from Manning for 39% off all Manning books. That's it, if you'd like. And now, the awaited moment when I'm gonna give you away 3 free e-books. Okay. If you'd like, you can do it now, and I'm going to show you the steps, how to do it, and the 3 discount codes. I was thinking how to best to do it, so I decided for the fastest finger, which is from, Who Wants to Be a Millionaire? There's a pre-step when you have to be the fastest. So whoever applies the discount code the first will be able to get the free book. So the steps are these. You go to the URL. Click on Add to Cart, but next to the e-book and not the printed book. Then click on the cart on the right upper corner and apply one of these codes. And if you go to the checkout before other guys do, so yeah, good luck. So any questions while some of you are trying to get the book? I'm going to get some questions if you like.
One question. It's a streaming process involving chunks of data of reasonably manageable memory loadable size.
Yes.
Have you tried, do you know any project, have you had any practical experience running this on a GPU?
No, I haven't done it. No, I think I've read something that some people have doing it.
Sounds feasible.
Yeah,
It's
yeah.
a streaming process of a chunk.
When you say streaming, you mean real-time data, or?
No, I mean you're doing one chunk and then another chunk and then another chunk, and you do a lot of chunks in parallel, non-dependent from each other, so you can use parallel processing of
Yes, yeah,
number
yeah.
of relatively simple CPUs. That's GPU by
Yes,
default.
there have been some efforts to do it with Spark, but I'm not sure how far they've come. Yeah. Any other questions, maybe? Yes. Okay. Thank you.